Greetings, it's Paul Bamberg with the introductory video for Class 16 of Math 117. Most of this is going to be devoted to pricing a single two-step call option, and it will introduce you to the important concept of conditional expectation. I've named this call option after Ed Purcell, who taught me quantum mechanics when I was an undergraduate, author of an outstanding textbook on electromagnetic theory, with whom I co-taught Physics 12B several times. Ed won the Nobel Prize for nuclear magnetic resonance in 1952. So remember how these scratch tickets work. There's a single scratch ticket. You can buy shares in it. And this is going to be a two-step scratch ticket, which means that it's scratched once 2 days before commencement, and then it's scratched again on commencement day, and the possible outcomes on commencement day depend on the intermediate scratch. This ticket is fairly priced at $20 2 days before commencement, and when it gets scratched, it's going to be worth either $30 or $15. We know these are fair prices, and this share can be traded on class day, as can a call option on it. The final scratch is made on commencement day, and on commencement day, if the ticket was worth $30 after the first scratch, it will go up either to $35 or down to $20. If, on the other hand, it was worth only $15 after the first scratch, it goes up to $20 and down to $10. You can buy a call option on this ticket. The strike price for that is $26. Now that's enough information for us to figure out the probability that the value of the ticket will go up or down on each scratch. We'll take advantage of the fact that the pricing is known to be fair. So look at what happens for node A. Either it goes up $10 or it goes down $5. If all these prices are fair, that tells us the probability of going up must be only 1/3, while the probability of going down is 2/3. From node B, it either goes up $5 to $35, goes down $10 to 20, and that tells us the probability of going up must be 2/3, the probability of going down must be 1/3. Finally, if it's worth $15 at fair pricing after the first scratch, the probability that it will go up $5 to 20 and the probability that it will go down $5 to 10 must be equal, so those probabilities are both equal to 1/2. So our sample space consists of 4 paths. There's path ABD, that has a probability of 1/3 times 2/3 or 2/9. There's ABE, that involves 2 successive events, each with probability 1/3, that has a probability of 1/9. ACE has a probability of 3/9, and ACF has a probability of 3/9. Now we have enough information to start pricing the call option. So far we've just considered the share price, and we have a sequence of 3 random variables. The initial fair price back on day 0, that's random variable x0, the price x1 on the intermediate day, and the price x2 on commencement day. These are random variables. Each of them has a value on each element in the sample space. And remember, an element of the sample space consists of a path, like ABE. The strike price is 26. The option is only worth exercising if the share is worth $35 on commencement day. If that happens, you will gain $9, and since we figured out that the probability of path ABD must be equal to 2/9 if the prices shown are fair. The fair price of the call option is 2/9 of $9 or $2. Now let's think about what happens after the first scratch. If the price goes down after the scratch on class day, there's no probability of its being ended in the money, so it becomes worthless. On the other hand, if it becomes worth $30 after the first scratch, then it has a significant probability of being in the money. So we can say the conditional expectation depends on what happens with the first scratch. Notice that if we don't have this intermediate step, we can't figure out the probabilities for reaching nodes D, E, and F. If all we know is that it is fairly priced at $20 on day 0, there's no way of uniquely assigning probabilities to the 3 possible outcomes on the last day. We need to know what happens in between. A bit of terminology here which will be important later. What we have here is called a Markov process. That means simply that the probabilities at each node do not depend on the history. In talking about the probability of going up or down from node B, well, here the history is you have to come from node A. But more generally, a Markov process refers to a situation where you have transition probabilities that don't depend on the history. This process is also a so-called martingale. We'll be spending 2 full classes discussing martingales. And what we mean by a martingale is that it's a sequence of fair games. The expectation doesn't change as you go from one day to the next. Now let's think about this scratch ticket as a simple example of a random process. It's a random process or stochastic process if you want to use a fancy Greek word. It's a sequence of random variables. Here there are only 3. Notice they're not independent. Simple proof of that. The event that x1 equals 15 certainly has a non-zero probability. The event x2 equals 35 has a non-zero probability. But there's no way that both those events can happen. If you have 2 events with non-zero probability, if they were independent, their intersection would have non-zero probability. So the fact that the intersection is impossible shows these 2 events are not independent of one another. We've also got an example of a filtration, a term that's been kicking around since the start of this course. We've got a sequence of 3 sigma fields that represent the information that's available on days 0, 1, and 2, respectively. And they're generated by random variable x0, by random variable x0 and x1 together, and by all 3 random variables. Notice you can't say that x2 alone generates the entire sigma field, because if I know that the value of x2 is 20, that tells me that the path was either ABE or ACE, but it doesn't provide enough information to disambiguate the 2 paths. We need the entire history in order to generate the sigma field for day 2. Now let's think about this scratch ticket in terms of conditional expectation. The fair price on day 0, given by x0, is equal to the expectation of the fair price on day 1. That is 1/3 times 30 plus 2/3 times 15 gives 20. If we want to check the fairness of the pricing for the second step, we need to do 2 calculations. Without fancy notation, we can say if we are in node B on day 1, the fair price there is the expected value of the random variable x2 on commencement day, and that's equal to 30. If, on the other hand, we're in node C, we can say it is the fair price determined from the knowledge that there's a 50% chance of either of these outcomes on commencement day. But the events, I'm in node B on day 1 and I'm in node C on day 1, generate the sigma field for day 1. We can rewrite this a little bit more formally in terms of conditional expectations. The hardest thing to get to understand about conditional expectation is that it's a random variable. So I'm writing now everything as a function of omega, as a function of which of the 4 paths actually occurs. And what I'm saying is that if the path is ABD or ABE, if it's a path that goes through node B, then the value x1 is equal to the expectation of the day 2 price given that we are in node B. That is conditioned on that element of the sigma field F1. Similarly, if the path is either ACE or ACF, the fair price on day 1 is the expected value of the random variable x2, conditioned on the fact that we were in node C on day 1. That is, however, not the usual notation for conditional expectation. Deneen is quite fussy in conditioning on sigma fields. What most authors do is just say we're conditioning on a random variable, and that's a valid thing to do whenever the sigma field is generated by that random variable. On day 1, the sigma field consists simply of the 2 events corresponding to the 2 possible values of the fair price on that day. So there'd be nothing wrong with saying that the value of random variable x1 for any particular path is the expectation of the value on day 2 contingent or conditioned on the value that the share had on day 1. The advantage of the first notation is simply that we can talk about a sigma field that's not necessarily generated by a named random variable. Don't try to use conditional probability as a guide to understanding conditional expectation. Conditional probability is just a number. It's the probability conditioned on some specific event having occurred. Conditional expectation, on the other hand, is not just a number, it's a random variable. It is something that assigns a real number to each element of the sample space, depending on which event in a certain sigma field has occurred. And in order to calculate conditional expectation, we need to know the conditional probability for each event in that sigma field. So let's use that idea to analyze the Purcell call option. Following Deneen's notation, I'm going to introduce 3 new random variables, v1, v2, and v3, and those are the fair price of this call option on day 0, day 1, and day 2. Each of these is a random variable, and we can work backwards to figure out their values. On day 2, things are very easy. If the ticket got 2 favorable scratches and is worth $35, then the call option is worth $9, and that will happen only if the element of the sample space that occurred, the path, is ABD. Otherwise, it's worthless, and our notation for this is it's x2 minus 26 plus, where the plus means if the value of this random variable is positive, keep it, otherwise replace it by 0. Day 1 is a little bit more complicated, but we've already figured it out. The fair value of the call option on day 1 is 0 if the path goes through node C. If the path is one of the two paths that goes through node B, then we can say the option has a probability of 2/3 of becoming worth $9, and therefore in this node the conditional expectation is V1 equals 6. Now we can work back to day 0. We can say on day 0 we look ahead and say there's a probability of 1/3 that the first scratch is going to make it move into node B. That is, it's got a probability of 1/3 of being worth $6. It's got a probability of 2/3 of becoming worthless, and therefore the fair value is 0. If I want to summarize this reasoning in terms of conditional expectation, I say for each element of the sample space, the value on day 1 is the expected value on day 2, conditioned on whichever node we're in on day 1. And similarly, the value of the random variable V0 is the expected value conditioned on F0, which is a particularly simple sample space because it's got only one element in it. Now let me re-express these ideas a little bit more generally, and let's introduce the complication that arises when we had the alternative of putting our money into the bank, and therefore we have to discount future values. So we've got a call option. I'm going to denote the maturity date by capital T. The strike price as usual by K. R will be the interest rate, and we're getting intermediate information at one time in between 0 and capital T. I will refer to that time as little t. When we're calculating and comparing expectations, we're going to reduce everything to values at time 0. That's not the only way to do things. We could compare based on values at time capital T or little t, but it's probably easiest to work at time 0. So now I can more generally calculate these risk-neutral probabilities. I say the value on day 0 is the expectation of the value at time t multiplied by the exponential of minus RT to move it back to value on day 0. Or alternatively, the value on day 0 multiplied by e to the RT to reflect the fact that we could have put money in the bank is the expectation of the random variable for time little t. Similarly, though slightly more complicated, the value at time t moved back to value at time 0. Sorry about that phone in the background. I should have shut it off. Is the expectation of the price at time t discounted back to time 0, conditioned on what happens at the intermediate time little t. Or, combining my two exponential factors, the value of the random variable x sub t multiplied by the exponential of r times the time that elapses between capital T and little t, the time that the money would be in the bank if we put it there, has to be the expectation of the value at time capital T. These equations will provide enough information to calculate the probabilities only if we have the same situation as we had for the Purcell scratch ticket. That is, there are only two possible prices at time little t, each of them in turn leading to only two possible prices at capital T. In the earlier example, there were two paths that led to the same price at time capital T. That's not a requirement in general. And similarly, for the value of the call option, I can say the value of the call option on day 0 is the expectation of its value at time t converted back to value on day 0. And that, in turn, is, for any path that may be followed, the expected value of the price at time capital T moved back to time 0, conditioned on what happened at time t. Finally, the fair value of the call option at time t is very easy. That's the maturity date. It is equal to the difference between the value of the share at time t and the strike price k, only counting situations where that random variable is positive. Now let me talk about conditional expectation a little bit more generally. To keep things simple, I'm going to assume that I've got a finite sample space. My sigma field is just 2 to the omega, and I'm also going to assume that for every element of the sample space, the probability is positive, so that there's no risk that I might inadvertently divide by 0. Let's think about a single event A and define a conditional expectation. What do I mean by the expectation of random variable x conditioned on event A? Well, I can calculate that by taking the value of the random variable for a specific element of the sample space and multiplying by the probability of that element of the sample space conditioned on the event A having happened. Here is a rewrite of that result. The conditional probability of the event element omega occurred conditioned on A is the probability of omega divided by the probability of A. I pull out the 1 over A. I am only summing over situations where event A occurred. So I have the expectation xdp, but I'm summing not over the entire sample space, just over the event A. Now, I need a random variable, so I have to think about everything that's in the sigma field generated by A. That's got one other event in it, namely the event A complement. So I can write down a similar formula for the expectation of x conditioned on A complement. And now you see how we do this. The difference is simply in whether we do our expectation calculation over A or over A complement. So we've got a sigma field consisting of 4 events: the unavoidable empty set and complete sample space, along with A and its complement. So let's consider an event in this with probability greater than 0. That means we have to exclude the empty set. And let's exclude the event with probability 1. That leaves just the event A and A complement. And they're a partition of the sample space, of course. Their union is the entire sample space, and they're disjoint. Any omega has to belong to one or the other. And so for either of these two sets, if omega is an element of B, the random variable conditional expectation of x conditioned on the sigma field A is simply obtained by taking the expectation computation using only event B and dividing by the probability of event B. This is the motivation for a key definition in Dineen's book. Well, that worked for the simplest imaginable sigma field, but it's not hard to be a little bit more general. We've got a probability space, a sample space, a sigma field, and a probability measure. And we're going to choose a sigma field G, which in general is a subset of the sigma field F. That's generated by some countable partition where, for simplicity, we're going to assume that the probability of each event in the partition is greater than 0. X is an integrable random variable, and for any individual omega, that has to lie in one of the events in the partition, has to lie in some G sub n, and so we define the expectation of X conditioned on the sigma field G to be a random variable whose value for any omega is simply the expectation of X restricted to the case where event G sub n occurred, divided by the probability that G sub n occurs. Most of the time, the sigma field will be generated by some random variable, call it y. Then G is just the sigma field generated by y, and instead of writing expectation of X conditioned on f sub y, most folks prefer to write just expectation of X conditioned on y. In other words, what's the expectation of random variable X conditioned on the fact that random variable y has had some specific value? While I'm not going to prove it, it's quite easy to show that in this case, the conditional expectation that we compute, a random variable, is also an integrable random variable. We'll be seeing lots more of this in the next class, but that concludes this introduction to the subject.